This section will provide a short introduction to pump types, operation, and hydraulic oil. The functions of hydraulic oil are to transmit power, lubricate components, remove heat from the system, seal clearances, inhibit rust and corrosion, act as a brake when required. The properties of hydraulic oil are viscosity, lubrication, film strength, pour point, flash point, demulsibility, resistance to foaming, chemical stability, anti-wear properties, compressibility. Viscosity is one of the most important criteria in the selection of a hydraulic fluid. There are two elements of hydraulic efficiency: volumetric and mechanical efficiency. Both of these properties are to a large degree viscosity dependent. The internal friction of the fluid will increase. This will result in increased resistance to flow. Component and fluid temperature will increase. Operation will be sluggish. Pressure drops throughout the system will increase. Internal and external leakage will increase. Pump slippage will increase and reduce pump efficiency and increase oil temperature. Increased friction between the moving parts will result in increased wear and more heat. The system will operate at lower pressure. There will be a loss of precise control. One of the most common problems with hydraulic systems is contaminated oil. Cleanliness of the hydraulic fluid and system is essential to maintain the longest possible life of the fluid and to ensure trouble-free operation. Sources of contamination: built-in dirt produced during repairs, ingress of rust, paint, etc. from tank or reservoir, generated in pump, valves, etc. Ingress from cylinder oil seals. Ingress from new oil and refill of oil. The importance of regular checks and replacement of line filters cannot be stressed often enough. There are two basic types of pumps: non-positive displacement pumps and positive displacement pumps. The positive displacement pump is most commonly used in hydraulic systems. A positive displacement pump delivers a specific amount of fluid per stroke, revolution or cycle. This type of pump can be classified as fixed or variable displacement. Displacement of pumps is normally given in litres per minute or cubic centimetres per revolution. These principles are the same for all positive displacement pumps. During the suction stroke, there will be an increasing volume inside the pump. This will create a negative pressure at the inlet port, which enables atmospheric pressure to force fluid from the reservoir and into the pump. During the delivery stroke, the volume will decrease inside the pump. This will force the fluid out of the pump and into the outlet pipe. A gear pump develops flow by carrying fluid between the teeth of two meshed gears. Gear pumps are referred to as unbalanced because high pressure at the pump outlet imposes an unbalanced load on the gears and the bearings. Normally they are used in hydraulic systems with pressure up to 20 megapascal. The two gears inside an external gear pump are placed side by side. A partial negative pressure is created at the inlet as the gear teeth unmesh, drawing fluid into the chambers formed between the teeth. The chambers carry the fluid around the outside of the gears, where it is forced out as the teeth mesh again at the outlet. During operation, the outlet pressure of the pump increases, and the gears are forced diagonally outward and against the pump inlet side. This pressure-force imbalance increases the bearing load on the gears, thus increasing wear, and may cause leakage. One of the most common types of internal gear pump is the gerotor pump. The inner gear is connected to the drive shaft and has one less tooth than the outer gear. This results in the outer gear rotating slower than the inner gear. The volumes between the rotating teeth increase during the first half of the revolution, taking fluid in. In the second half of the revolution, the fluid is forced into the discharge port. The pumping chambers are formed between the vanes and are enclosed by the rotor, ring, and two side plates. Normally, vane pumps are used in hydraulic systems with pressure up to 20 megapascal. The slotted rotor runs eccentric to the casing. Movable vanes are fitted into the slots, and during rotation, centrifugal force, or the pump outlet pressure can be directed to the backside of the vane, moves the vanes outwards. Each pair of vanes forms a pumping chamber that varies in volume as the pump rotates. As the chamber passes the inlet port, it enlarges due to the eccentricity of the cam ring and rotor. This creates a negative pressure that allows fluid to be pushed into the cavity by the atmospheric pressure in the inlet line. As the rotation continues, the volume of the cavity is reduced, and as the pumping chamber reaches the outlet port, the fluid is pushed out of the pump and into the system. Balanced vane pumps are designed to reduce the unbalanced bearing load. It has two inlet and two outlet ports. The rotor runs within an elliptical casing. With the two high-pressure ports being directly opposite each other, the resultant radial forces are equal and opposite, which virtually eliminates the bearing wear due to loading. The advantage of the pressure-compensated variable vane pump over the fixed displacement type is energy conservation. When no or very low flow is required in the system, the pump automatically adjusts accordingly. Maximum displacement occurs when the greatest eccentricity exists between the rotor and the cam ring. Displacement of the vane pump can be varied manually by an external control, such as a hand wheel, or automatically by a pressure compensator. The pressure compensator senses the pressure in the system and adjusts the pump displacement to maintain a preset pressure level. The two basic designs of piston pumps are radial and axial. Both are available as fixed or variable displacement pumps. Axial pumps are used on systems with pressure up to 35 megapascals. Radial pumps are used on systems with pressure up to 70 megapascal. In axial piston pumps, a number of pistons reciprocate within a cylinder block, parallel to the axis of rotation. The best known of the axial piston pumps is the swash plate pump. The cylinder block is driven by the drive shaft in a fixed position. The pistons, which are fitted into cylinders in the drive block, are connected by piston shoes to the angled swash plate. As the block rotates, the shoes follow the course of the swash plate, causing the pistons to reciprocate within the cylinders. As the pistons move outwards, a suction port is formed and oil is drawn into the cylinders. As the pistons continue to rotate, they move inwards due to the angle of the swash plate, thus discharging oil. The discharge and inlet ports are located in the valve plate. The displacement of the pump varies according to the swash plate angle, the size and number of pistons, and the speed of the pump. The control consists of a yoke return spring, which returns the yoke and the swash plate to the full delivery position. This spring acts against an oil pressure-operated compensator piston, which is extended by the system pressure and is in direct opposition to the return spring. Startup. As there is no system pressure, the spring pushes the yoke and swash plate to the maximum angle, thus ensuring maximum flow on startup. During operation, when the pressure increases within the system, it overcomes the spring pressure and moves the yoke and swash plate back towards the minimum flow position until equilibrium is reached. If the pressure decreases, the spring overcomes the oil piston pressure, causing the yoke and swash plate to move to a greater angle. In this way, the compensator adjusts the pump output to whatever level is required to develop and maintain the preset operating pressure, avoiding relief operation at full pump volume during holding or clamping, thus preventing power loss. The principle of this pump is the same as that of the swash plate pump. In this pump, the cylinder block rotates at an offset angle to the drive shaft. The cylinder block is attached to the drive shaft by means of a universal joint to maintain constant alignment and to ensure that they rotate at the same speed. The universal joint does not transmit any torque except for the acceleration and deceleration of the cylinder block. The pumping action is produced by the reciprocating pistons. The pump displacement varies with the offset angle. Fixed displacement pumps are usually available with 25 or 30 degree angles. With variable displacement pumps, the offset angle can vary between 0 and 30 degrees. The angle of the yoke is controlled through an external linkage. With some controls, the yoke can be moved over the center position to reverse the direction of flow from the pump. In a radial pump, the cylinder block rotates on a stationary pintle inside a circular reaction ring. As the block rotates, the pistons will follow the inner surface of the ring. This ring is offset from the center line of the cylinder block. Porting in the pintle permits the piston to take in fluid as they move outwards and discharge it as they move in.